All right. Good morning, good afternoon, everybody. So my name is Serguei Tchessalov. I'm a research fellow with Pfizer. Um, I was graduated in 1983 with engineering degree in cryogenics from Moscow Technical University, and I immediately started working at Institute of Applied Microbiology in freeze drying. And since 1983, that's what I essentially do. In 1993, I got my PhD in biotechnology engineering. My dissertation was dealt with mathematical description of pressurized test, which known as MTM now. In 1999, I moved to Connecticut, joining Michael Pical lab as a postdoc. And I worked for a couple of years there. It was a really great time. Then I moved to Seattle, working for Immunex, working with one of the first top biologics, Emperor. And then I moved to Wyatt in 2002, and then back to the East Coast. And Wyatt became Pfizer in 2009. At Wyatt, Pfizer, basically my interest was scale up and tech transfer of lyophilization processes, and especially with assistance of mathematical modeling. In 2012, I was start interested in alternative drying technologies, alternative to vial freeze drying, and that's what something I would like to share with you today. So, okay, try to move. Okay, it's moving now. So what we'll be talking today, some advances in the spray freeze drying, touch a little bit on spin freeze drying, and a little bit on foam drying. Spray freeze drying. I'm talking about on behalf of a large team. Some of team members are listed there from Pfizer as well as from Meridian Technology. So let's take a look on both conventional vial freeze drying process and spray freeze drying. So in vial freeze drying process, what we do, we fill relatively accurately vials with liquid product. We move vials on the shelf, cool it, freeze it, apply vacuum, dry it, stopper, and seal these vials. In spray freeze drying process, you actually kind of do reverse operations. You first spray freeze it particles, then you dry them, and ending up with very nice flowable powder, which you can actually later fill in any type of container, as you can see, vials, dual chamber, bottles, bags, blisters, whatever. So if you compare these two technologies, for example, freezing time, it takes only seconds to freeze small particles about 0.5 millimeter, and it's very useful for products that require very fast freezing. Drying, because of small particles, you can dry about 40 times faster than you do the same product in a vial, and actually you can do successfully very low collapse product, even below minus 40 degrees Celsius can be done by spray freeze dry. In the reconstitution, we demonstrated that you can do as fast as 7 times faster in spray freeze dry powder as compared to vial freeze dried product. Yes, accuracy is a little bit less than liquid product, but it's still good enough to deliver dose, required dose. Aseptic, yes, both technology can deliver aseptic product. And in terms of flexibility, yes, spray freeze dry, it definitely provides much more options as compared to vial freeze dry. So what we have currently is, in terms of from a commercial point of view, we have 2 companies that can make commercial scale equipment. One of them is Meridian, In the Meridian technology, what you have a large column, chilled column, in which you spray liquid product. It freezes, then it's collected in a drum. Frozen pellets, once filling spraying process completed, valve is closed and applied very deep vacuum. You would be surprised, you can get up to 5 millitorr. And then you provide heat through infrared radiation and contact at very low vacuum conditions while rotating drum. And when process is complete, which you can use pressurized test, Pirani versus capacitance manometer, you basically remove product into container closure, which you can move anywhere to fill inside. So in EMA-Life, they have essentially the same freezing process. It's a low temperature column, but in what they have two condensers, and that's allowed to do continuous spray freeze drying process. You freeze particles, you collect them in intermediate chamber, and then you dump them into a drying chamber, in which you have some sort of conveyor that you move frozen pellets until they actually dry. I suggest you to look at a link there and some details you can grab from their website. Okay, so what we've done so far in terms of spray freeze drying, and we did local collapse products. Temperature, collapse temperature was below -35 degrees Celsius, and we get moisture below 0.5%. And with some products, we see some turbidity after reconstitution, but if you add some surfactant, it's typically goes away. With spray freeze drying, you get very high concentration. After lyophilizing this, you can reconstitute with less volume, get to about 200 mg/ml or above. And if you compare recon time, vial versus the same amount of spray freeze dry powder, it can be done 7 times faster, which could be important. We tested it, like, because we see impact of surfactant. We tested to what degree surfactant works, and we increased concentration up to 2%, which in the product that was turbid allowed decrease particle number of particles above 10 micron, decreased by factor of 100. But still, some of the solution remains slightly turbid. So keep in mind that it can work, I mean surfactant, but not for all products. Particle size. It is, if you, for example, have 30 micron particles versus 700 micron, it's for column, it really doesn't matter. And you can, by having large particle size, larger, you can increase throughput by doing that. And we tested what impact of this particle size on the flowability, and we found there is, at least in the range between 300 700 micron, was no impact. Just a little bit of longer recon time for 300 micron particles, but that was not significant. So stability, product tested with 3 monoclonal antibody. Product was stable for 2 years, very comparable to vial freeze drying process. LNP, we also tried LNPs. It's also comparable product to a vial freeze dried material, and it's stable for at least 1 year. Yes, it does increase some particle size after spray freeze drying, but if you do annealing, that will effect go away. We also tried small molecules in a few of them, and we demonstrated that yeah, it's good quality, but recon time can be significantly decreased. So as you can see, we applied this technology for different modalities. We also tried this spray freeze drying of some of our product at a large scale, which is available at Meridian. We tested product in a protein range, concentration range, 50 to 150 mg/ml, and the particle size range 0.6, 0.8 millimeters. And we got about 80 lost 83% of yield. The reason we lost the product was some of clogging in the column, initially at least, during a long spraying process. But that can be eliminated by just lowering temperature of this intermediate chamber between column and the drying chamber. Stickiness, if you dry at high temperature, so it seems like if product exceeds slightly glass transition temperature, TG prime, then it can stick to the wall. So if you reduce pressure and reduce product temperature, that goes away. Attrition, yes, particles remain in the drum, and some frictions occurs, and that can result in a small dust, a small particle dust. So the smallest time you hold this particle in the chamber, and the less impact. So we tried also very challenging, I would say, material, sucrose sodium chloride. Some of these products can very hard to freeze dry in a while. When we started doing this work, we just get initial yield about 64%. And that was mainly due fluidization toward end of drying. So you can see like sandstone. The sublimation rate is so high that and particles become so light, so it just carry out to condenser. So that's why we were losing so much product. But by implementation of some PT tools and modification of drum and mixing process, we were able to reduce this impact. Electrostatic, so can be also removed this effect by implementing anti-static device. With all of this implementation, we were able to get consistently yield more than 97%. And we tried this dry pellets with two companies that make powder filling equipment, and we get accuracy better than 1.7% in the range of between 10 and 57 milligrams. So you can see that we demonstrated also that this different modality can be produced at large scale with high yield and filled accurately in any type of container. So another work that we did is to demonstrate that this technology can produce aseptic material. So back to 2018, I presented first work from Meridian when they attached different about 29 thermocouples in different locations within spray freeze dryer. And we are able to demonstrate that you actually can reach desired temperature about 120 degrees Celsius for at least half an hour. So basically successfully sterilizing internal surfaces of a dryer. The challenge was that, and question come out, yes, you can do all of this, but nozzle diameter is very small. It's about 0.3 millimeter. And then how you can control that. And so the next step was sort of testing was to demonstrate that that you can actually aseptically deliver solutions through this nozzle and the steam sterilized clean, and that could be done in a robust manner. So what we did is you can see on the right is that is essentially we took nozzle from the column, put in a vessel which had some jacket, and we can control temperature of this vessel. It has also steam sterilizer, steam generator, deflection gas filter unit, and it's also has a liquid pump to remove product from that vessel. So what we did, we use perform a few tests. In the first test, we just simply add the incubation solution CASO to this through the filter into this vessel. Wait for 3 days at 35 degrees Celsius, nothing happened. So we demonstrate that it can be sterilized and kept sterile in a vessel. Then second test, it was in a line, so intentionally contaminated with sparking microorganism, Bacillus subtilis. And then after that, it was basically added as incubation solution, incubated. You can visually see that growth demonstrated, yes, you can promote the growth. In the test number 3, we did all of this, plus we, after it was incubated, we steam sterilized it, clean it, and added incubation solution, wait for 3 days, nothing happened. So we demonstrated that it can be cleaned and sterilized. That was all 3 tests were done with without nozzle. So test number 4, when we add a nozzle to this process and contaminate it through the nozzle, perform all of this testing again and demonstrate that, okay, even through the nozzle we can contaminate, clean, steam sterilized, and the product could be sterile. In the test number 5, last one, we, in addition to that, we also contaminated deflection lines, and all this process was done exactly as all tests previously, except that we hold for about, I think, 7 or 8 days at 35 degrees Celsius. To make sure that nothing grows at all. So we demonstrated that product can be done in a aseptic way. All right, so you need to also understand your process very well. And you can do numerous experimentations. And we, at that time, we already purchased lab scale equipment from Meridian. You can do a lot of experimentation to understand what your design space, or you can, in parallel, or replacement, to do some modeling. So first we did some CFD modeling of column, and you can see some results of this. And we demonstrated that if you just spray without spreading these particles, the particles, when moving down toward the bottom of column, when solution crystallizes, release heat. And that heat could impact how particles above are moving, and they just can coalesce, so get to each other and form larger particles. And to eliminate that or minimize that, it was a deflection applied to this stream of liquid. And you can see that these particles are spread within the column, which A, improved freezing, and B, allow less possibility for them to stick to each other. So we also learned that because of temperature at the bottom of column is higher than right at the exit is higher than in the bottom of column. So you do see some flow from the bottom to the top that could also impact particles movement within the column. So that's all of this was as input parameters into the model. You can see that that's our outcome of this modeling, where you can see impact of, for example, in this particular case, temperature, column temperature. If on the y-axis it's a freezing distance, the column, and on the x-axis is droplet diameter in millimeters. For example, for half-millimeter pellets, in order to, for example, freeze product below minus 50 degrees Celsius, you need to have a column about 3 meters. But if you decrease column temperature to minus 150 degrees Celsius, you only need 1.6. So it tells you what is help you to design proper diameter and proper length of column. So to confirm this model, we did some experimentations, and we just simply put some cone made of styrofoam inside a column at a certain distance, and we collected frozen pellets, measured temperature of these pellets, and compared to the results of modeling. You can see they align quite well. So we were confident that we have very robust model of spray freezing. In terms of drying, we working on generating input parameters, like for example, resistance of within small pellets, as well as heat transfer coefficient from a heating surface to the pellets itself. For that, we use a Milrock micro freeze dryer, which has heat flux sensor. So hopefully we'll get some results on the input parameters that we can put in the model. Okay, that's a modeling, and that brings me to sort of a summary slide on what we've done with spray freeze drying and what's sort of maturity state. And as you can see, we've done a lot of work on lab scale. So stability is good. We have commercial equipment. We do understand very well spray freezing process and drying process. We're still working on that. We've done some tested commercial freeze dryer. In terms of infrastructure, you know, the most of sites do have liquid nitrogen supply, but of course, it's also required building additional infrastructure plus some powder filling lines. In terms of regulatory awareness, so you can, of course, have very nice technology, everything is done, but if regulatory never heard about this, you will probably have some challenge. Excuse me. So, but we presented at least 3 times to FDA as this technology, both Meridian and EMA, and I think they were very happy with this results. Okay, that's spray freeze dry. Okay, let's move to spin freeze drying process, and I'm speaking again on behalf of large team at Pfizer and Reavita. So in spin freeze drying process, what you do, you just take a vial, same vial that we use in vial freeze drying process. You spin it. In our case, it's about 4,000 RPM, which make it very thin layer on the wall. Then you apply your cold nitrogen to wall, and you freeze it at the rate actually you really want. It's really, you can do a very wide range of freezing rates. Then you have infrared source of heat while you provide to the vial while you're rotating vial. So again, allow some very homogeneous drying process. And once primary drying is done, which you can detect with EIR, you can raise the temperature to secondary drying, removing water. And you can see through the bottom of this vial, which helps to let's say to visual inspection. So it's what's the benefit of this is, of course, it's you have controlled freezing. Every single vial essentially done the same way. That's important. Freezing profiles are very different. You can very wide range of freezing rates. You can control every single vial, and because of high surface and thin layer, you can dry very fast, about 40 times. And so we put like pros and cons of this technology on this slide. And first, it's continuous process, which minimize some errors. It's while feedback control during process. So again, every single vial can be controlled. It's faster drying. Visual inspection is really improved, 40 times faster. The problem is, I don't know if it's a problem or not, it's low throughput compared to large freeze dryer. But that's may not be problem if you have, let's say, very expensive product which you don't need high throughput. Let's say you need to make like only 500 watts, okay, for gene therapy or even for some very expensive products. So that could be equipment to use. However, it has some complexity, of course, with a lot of mechanical parts, like moving parts, some vacuum load locks, and so that creates some possible challenges. So we try this technology on a few products. It's LNPs, trying to understand if we can, by changing freezing rate, can increase percent of encapsulation. And with AAVs, adeno-associated virus, we want to make sure that we can provide faster cooling rate that hopefully we hope that that can help to stabilize AAV. We also try this for some of protein, and we checked if we can eliminate aniline, for example, for mannitol containing formulation. So there is some results shown on this slide. Let's focus on first on LNPs. You can see that on the percent of encapsulation on the left and concentration right. After lyophilization, we can see the drop in percent of encapsulation, which was also similar with spin freeze dry. So we didn't really benefit of faster freezing. But if you add aniline, you can see there's some improvement, which, to be honest, I'm not sure it has to do with variability, I'll say, or maybe it's true impact. So if you look at virus, then you can see that what was a surprise for us, so for some reason, we see some increase in high molecular weight as compared to vial freeze-drying process. Particle size was, the number of particles was decreased, but we still see some negative impact, at least on this AAV that we used. So the conclusion was that further evaluation is needed of this technology in application to this type of product. We also tried, again, protein, see if we don't need aniline. Unfortunately, we see some mannitol hemihydrate without aniline step, so it's obviously the unit need to be modified in order to allow aniline step during process development. Okay, so what is available now? It's slides from Reavita, so single vial unit that we have now, and it's available. Same as a multi-vial unit, I think they can make about 100 vials in this unit at the University of Ghent. I've seen by my own eyes, it's working very well. I heard that they build already a commercially scale GMP grade line. It's probably just in process of validating at this point. The company Reavita, as well as Ghent University, in particular Thomas de Beer group, they do work on LNPs as well. And here's a couple of publications they shared. So go ahead and take a look at this publication. What they demonstrated that it's spin freeze dry can be used for making dried LNPs, which are stable. So there is a benefit. They mentioned that is continuous, it's very fast process, it's efficient, safe. There's at least no batch rejections because you only, if some problem, you reject the vial, not the entire batch. They have very good models, so that they can understand the process very well. Using this unit, you can do very fast formulation process development. It's very flexible. You can change between different type of vials. And according to this company, you can get faster to market, at least reduction of this time. It's about 1 year, according to them. And it reduces ecological footprint and operation cost. And if you go to the next slide, you can see that according to Reavita calculations, that the cost energy would be twice less, okay, use of energy for this technology as compared to vial freeze dry, regular vial freeze drying process. Okay, so let's just compare maturity state of this technology. Okay, then let's move the box. Okay, so all right, so it's shown for multiple product, it works. Stability, I think we're still in process of evaluating. While they claim they build commercial scale equipment. I don't think it's operational yet. So, but hopefully that will change to yellow very soon, or green. Process understanding, yes, models are developed and validated at laboratory scale, need to be confirmed at commercial scale. Because equipment was not available, nothing was done at commercial scale yet. In terms of infrastructure, yes, liquid nitrogen lines available at sites, so it can be relatively easy implemented. The benefit of this technology as well, that you can put in literally in the center of a field, and as long as you have all the supplies, you don't need any control of environmentals, because everything is contained inside. So that's good. So if you put this equipment, for example, in your existing facility, you don't need Class A. That's a point. I think it's a significant benefit as well. A regulatory agency, FDA, at least aware of this technology. They hear it many times, so that's also will help to promote it. So with that, let me move to foam drying. So again, I speak on behalf of team from St. Louis, Armando, Alex, James Searles, Kate, and Satoshi Otake. So foam drying. Foam drying was known for forever. I think the middle of 50s, and even for, it's always been like a sort of negative. I think the formation of foam during lyophilization was kind of considered as a negative, until I believe in 2000 was patent. I think the group led by Bronstein, where they demonstrated that this technology can be widely used for different type of products, and they have a lot of patents on that. So we try to evaluate this technology for the product that really sensitive to freezing. Okay, that was essentially idea for this technology, I believe. What you can do also, it's very fast dry. Well, by foaming, you create a lot of evaporation surface, and the primer drying, if you consider it's a primer drying because it's never frozen, then the most sort of initial evaporation step is very fast, and then once you remove this majority of water, then you start to remove at moisture during secondary drying, and it's even with that, it takes longer time than normal secondary drying, but even with that, it's still short the process. Okay, the challenges is non foam formation is not homogeneous, unfortunately, and I will show this later. And it's very difficult to replicate this foam in the large scale. At least I have not seen it. So there was also limited work studying design space, at least in terms of wasn't published a lot, even by Bernstein's group. However, if you look at some impact of this foam drying on different modalities, you can see some positive impact, for example, on T cells. On the left, you see the graph at work performed by Pfizer internally. You can see that if you foam drying this, they are relatively stable, and stable compared to initial, as opposed to a regular vial freeze drying process, which done to the moisture content similar to that in foam drying. So yes, that's some of products don't like freezing. Same, for example, measles vaccine. You can see literature data that foam dried measles vaccine was much more stable than lyophilized vaccine. Again, foam drying, unfortunately, it's not really reproducible in all vials. You can see that every single vial looks differently. We tried with LNPs, and we also tried gene therapy products, about 30 formulations that we tried, and you can see that it's really not the same. With that said, so let's look at with that said, we get some positive results on some products, as I mentioned, but with LNP and gene therapy, we didn't have a luck. So lyophilized samples, for example, for gene therapy product was more stable than foam dried product. Okay, so if we compare this technology to spray freeze drying and spin freeze drying, yes, it was shown that some proof of concept for some of products. Not for all of them, but for some. Stability, we're still evaluating that. The key point is that you need to really to get to low moisture in order to have long-term stability. So the secondary drying must be long. We don't have models. We don't have, of course, we didn't test on the large scale successfully. In terms of infrastructure, so we do have actually existing equipment can be easily converted into foam drying. All you need is you have additional valve, for example, of course, some filter, and you need to adjust software that allows you to control pressure between 1 and 10 torrs. That's a pressure range in which you make a foam. So that's relatively easy to convert any existing freeze dryers in foam drying, as long as you have to demonstrate for some of your product that's really good technology. And in terms of regulatory, I presented it last year at IFPAC, and there was a lot of FDA people. They were interested in that, but I think they have some questions about reproducibility of this process. So, and again, as I mentioned, that's really challenging at this point. So I would like to acknowledge a lot of people that contributed to this work, from Pfizer, Purdue, Meridian, Reavita. And with that, I'm ready to answer all the questions.